Hello, welcome to Zigmatech Learning Hub. I will be your instructor for physics. For this class, we are going to be taking our exercises from Examguide app. If you don't have the application already installed on your device, I will want you to download the app in order to follow along in this class. Examguide is a leading educational app that helps students prepare adequately for various exams like UTME, post-UTME, WAEC, JCE, KCPE, IJMB, JUPEB, KCPE, BECE, JSCE, NCEE, NECO, etc. You can download the app from www.examguide.com or Google Play Store. Please subscribe to our channel and turn on the notification bell and get updated on new videos. Are you ready for this class? Okay, let's get started. Welcome to physics class on Elasticity Part 2. We have studied elasticity for the first one, which we titled Elasticity Part 1. In that Elasticity Part 1, we looked at Hooke's law, what Hooke's law stated about material that can be extended when force is applied. And what you're watching on the screen is also one of the clips to trace the point we treated in the first part. And it simply means that when a force is applied on an elastic material, what it does is to extend according to the force applied. The more the force, the more the extension. In this class, we're also going to say, just like I said earlier, that so many materials are supposed to extend and return to its original shape. And that is why you and I will be able to enjoy going past the top of a bridge, because the materials used have the ability to extend and return to its original shape. There are some bodies that are supposed to be stable, while some are supposed to accelerate, while some are supposed to extend and return to its original shape. All these are the applications of the elasticity to real-life experience. Now, there are some other parameters you have to consider for you to be able to understand what this elasticity is. Now, before you end this class, you should be able to define tensile stress and strain, define Young modulus, and explain the work done in a spring or work done in an elastic materials. Now, when we talk about tensile stress and strain, we are talking about a tension, because from the word tension, we have tensile stress. And I also want you to know that when you talk about stress, we're also talking about pressure, because they all have the same unit. Now, you know what is a tension on what you learned before, which is a force applied through a rope. But at this point, when we are talking about the tensile stress, mathematically, we are talking about the force applied on an object and the unit area where the force is applied. For example, looking at this you're watching now, you see that a force is applied at a given surface area. So it is all about the force applied and the area at which the force is applied, and that is what is called the tensile stress. Now, we also have another one we call the tensile strain. When we're talking about the strain, we are looking at when this force was applied, what happened to the object? The object increased in length or decreased in length because of the force applied, and then that change in length divided by the original length is what tensile strain is talking about. So that is why we have this as this change in length, and this is the original length. So we now say that stress or tensile stress is giving us force per unit area, which is the same thing as force is in Newton and area is in meter square. So we say that the SI unit of stress is Newton per meter square. Then when we talk about the tensile strain, this is what happens inside the material. So we are talking about the change in length all over the original length, or somebody will say the extension, E2 minus E1 all over the original length, which is L1, or maybe L sub naught. So that is what mathematically what we look at when we are talking about this tensile strain. And I want you to know that this tensile stress or tensile strain, these are all qualities of deformation or force applied on a body. So we are simply saying when you apply force on a body, like you are sitting down on the chair or you are driving with your car on the road. So all these things you are doing, you are applying a force to a particular surface. So these are all natural applications to the tensile stress and tensile strain. Then look at this again, which you have seen before. This is very important, that this body or this plane has to return back after a force is applied. If not, there will be no bridge. If there is no material that can extend and return to its original shape, then we may not have bridge, you may not have chairs to sit down. So this force applied to this material helps the material to maintain the balance. Now we are going to look at the first question. We said that a force of 40 Newton is applied at the free end of a wire fixed at one end to produce an extension of 0.24 millimeter. If the original length and diameter are 3 meter and 2.0 millimeter respectively, calculate the stress on the wire and the strain. So we already have the formulas written on the screen on the board here. So what we are going to do is we have to do some conversion, because see, if you look at this, this is in meter and this is in millimeter. We have to do conversion from meter to millimeter, or from millimeter to meter, and which is the right thing is to do conversion from millimeter to meter. And if you watch our previous videos, we now say that 1000 millimeter make 1 meter. So in this case, if I have, therefore it means that 1 millimeter is given as 1 over 1000 meters. So how do I convert 2.0 millimeter to meter? I'm going to say that 2.0 times 1 over 1000, which is going to give you 0.02 meters. And that is the what? The original length. So that is going to be the diameter. Diameter is going to be 0.02 meters. Then when we talk about the original length, L sub naught is going to be 3 meters. Now, we also have an extension, E. Extension was given at 0.24. (0.24) times 1 over 1000. So this is going to be going, we now have 0.0024 meters. This is going to be another 0. So this is going 1, 2, 3, 1, 2, 3. Yes. So this is going to be the extension. E is going to be this. Then L sub naught is going to be 3 meters. And then I'm going to have that 2R. Remember that diameter is 2R. 2 multiplied by the radius is diameter. Is going to be 0.02 meters. Therefore, radius or R is going to be 0.01 meters. So all these parameters are going to be vital in our problem solving. Now, what are we to find? The first thing we are asked to find here is the stress on the wire. And we said that the stress is equal to the force all over unit area. Now, if you look at this question, they gave us diameter, and they gave us extension, and they gave us original length. So, it is a wire. So we are going to look at the wire as a circular cross-sectional area, which is what you are looking at. And if the cross-sectional area of a wire, like this marker, the circular part of it, then we are going to look at it as a circle. So the area is going to be the area of a circle, which is going to be force all over pi r square. So I'm going to have that force given here is 40 divided by, so divide by 3.14 multiplied by radius is 0.01 all squared. So the stress is going to be 40 all over. So I'm going to have 3.14 multiplied by 0.01 times 0.01. So I'm going to have 0.000314. So the stress is going to be the stress is 127388.54 Newton per meter squared. So that is the stress on this question. That is for the A part. That is number 1. So let's go to number 2. And number 2 is talking about strain, and the strain means extension all over original length. And original length is 3. And what is extension? Extension is already given here as 0.00024. So when you now simplify 3 into this is 8, you have 0.0008. In this case now, because remember that extension is in meter and length is also in meter, so they cancel out. Therefore, the strain is not going to have any unit. So we are going to look at the second question. Now let's talk about Young modulus of elasticity. When we talk about Young modulus of elasticity, we say that the Young modulus, this symbol for Young modulus is given as stress over strain. So we are going to say is a ratio of stress over strain. However, you can also say that stress is directly proportional to strain. So we say that stress is equal to K strain, whereby this K is a constant. So we are saying that when stress is directly proportional to strain, the constant of proportionality is given as the Young modulus, and that is it. And Young modulus is defined as the ratio of the stress to strain. So if we now put the formula, we now say that the Young modulus is given as force over unit area, all divided by the extension all over original length. So we say that Young modulus is this F over A divided by extension over original length. So Young modulus is going to be F over A times original length over E. So this is FL all over A E. So this is the relationship given for Young modulus. And we are going to be using this expression throughout this class. Now, we have a question here. It said a wire of 2 meters and a radius of 1 millimeter is stretched by 25.0 millimeter on application of a force of 10 raised to power 3 Newton. Calculate the Young modulus. So we are given the length. So I'm having a length which is 2 meters. And I'm having a radius. The radius is given as 1 millimeter. So I have to convert millimeter to meter. So we say that 1,000 millimeters is equal to 1 meter. So 1 millimeter is the same thing as 1 over 1,000 meters, which is 1 millimeter is something as 0.0001 meters. So the radius is going to be 0.0001 meters. Then is stretched by, that means the extension is given as 25. So I'm going to have extension which is given as, if 1 millimeter is 0.00015, then I'm going to convert 25 times 1 over 1,000. Remember, 1 over 1,000 is something as 1 millimeter. Then I'm going to have 0.25 meters. It's going to be 0.025 meters. That is going to be the value of this extension. So this is 0.025 meters. So when I have this as the value for the extension, then I have that the force is given as 1,000, which is something as 10 raised to the power 3. The Young modulus is given as force over area divided by extension over original length. And that is going to be force is 1,000 all over area. In this case, you have to find the area because the radius is given there and it is of a wire. So we are looking at the cross-sectional area of a wire, which is a circle. So this area I'm going to put here is going to be pi. I'm going to say the pi is 3.14 times the radius, which is 0.001001, then squared, because the area is given as pi r squared. So the Young modulus, let me simplify here then. We talk about the extension and the original length. So this should be 0.01 meters. So 0.01 meters. So having 1,000 divided by 3.142 times 10 raised to the power 5. This is going to be minus 5. So I'm going to write this one as 10 raised to the power 3. So this is going to be, then I will divide this by the extension, which is 0.25 divided by length, which is 2. So this is going to be, Young modulus is going to be 10 raised to the power 3. That is 1 times 10 raised to the power 3 divided by 3.142, then plus 5, because this minus is dividing the same base, they will now subtract each other. So minus 5 will go and become plus 5. Then this is going to be times 2 all over 2.5 times 10 raised to the power minus 1. Right? Because I have to convert this to fraction. Remember, in ordinary fraction, when you are dividing, the denominator goes up to become, and then the numerator comes down. So I'm going to have that the Young modulus is given as 2 times 10 raised to the power 8 all over 3.14214 times 2.5 plus 1. And this is going to be equal to So I will still maintain 2 times 10 raised to the power 9 all over 7.855. So let us end it here. So the Young modulus is going to be equal to 2 times 10 raised to the power 9. So I'm going to divide 2 divided by this first. Then whatever I have, I'll multiply it by 10 raised to the power 9. So 2 divided by 7.855. I'm going to have 0.25 times 10 raised to the power 9. So Young modulus is going to be, this is 2.5 times 10 raised to the power minus 1 times 10 raised to the power 9. So the Young modulus is going to be 2.5 times 10 raised to the power 8. And what is the SI unit of Young modulus? we can derive the SI unit of JAMB modulus by simplifying this. And I'm going to do it here. So JAMB modulus is given as force, which is Newton per meter squared, divided by, everything here is 1. So I'm going to have that the JAMB modulus is Newton per meter squared. So this is going to be 2.5 times 10 raised to power 8 Newton per meter squared. Thank you for being part of this class. Remember, before we go, we have a few more exercises bringing to you through the Examguide app. We have the first question here. We have an elastic material. Elastic material has length of 36 cm when a load of 40 Newton is hung on it, and length of 45 cm when a load of 60 Newton is hung on it. The original length of the string is. So we have the first one, which is 36 cm. So that is going to be the original length. The elastic material has length of 36 cm when a load of this one was hung on it. So I'm going to look at it as just the length based on the extension. In this case, I'm going to say that extension is going to be equal to L2 minus L1. So L1 is going to be the original length. Therefore, I'm not going to use this 36 as my extension because it is just what was extended when that force was hung on it. Therefore, I don't know the extension and I don't know my original length, but I know L2 because this 36 is what extension gave you. But then I have to convert it to meter. So 36 divided by 100 is going to be 0.36 meters. So I'm going to have that E is going to be equal to 0.36 minus L1, equation 1. Then what force gave this? F1 is going to be 40 Newton. And that is the force that gave this. And on it, and a length of 45 cm when a load of 60. So there is another one. So L2, another extension. So I'm calling this one E1. Then extension E2 is going to be 45, which is going to be 0.45 minus the original length. So this is the E2. Now we are asked to find the original length, and the new force F2 is going to be 60 Newton. So now what are we going to do? Remember the equation. Remember the equation according to Hooke's law, who stated that F is equal to KE. So in this case, I'm going to use the first one, which is 40 is equal to K bracket E is 0.36 minus L1. That is the first one, equation 1. And then 60 is equal to K bracket 0.45 minus L1. And this is equation 2. So I'm going to divide the equation 2 from equation 1. But if I do that, I am going to know. So let us open the bracket first. What I'm going to have is 40 is going to equal to 0.36 K minus KL1 and also going to have that 60 is going to be equal to 0.45 K minus KL1. So we have something that is very similar here. We are having that K is here and K is here, so which was supposed to be factorized. Okay, so I'm going to say, if I say equation 2 minus equation 1, I'm going to have 20, because 60 minus 40 is 20, which is going to be that. So if I minus, will I be able to eliminate this? Because I want to have one, at least constant is what I'm looking for at this point. So if I say L2, equation 2 minus equation 1, I'm going to have minus KL1 minus KL1. Yes, they are going to eliminate. So we are in the same track, in a very good track. So I'm going to have 0.45 minus this. So 0.45 minus 0.36. So 15 minus 6, we're going to have 9. So what is remaining here is 3, so 0.09. So I'm going to have 0.09 K. This and this will cancel out. Therefore, we say that constant is going to be 20 divided by 0.09. So K is going to be so K is 222.2, and that is going to be Newton per meter. All right. Now, after that, we have to substitute this value in any of this equation, either this equation or this equation, to be able to get our original length. So I'm going to have 40 is going to be equal to 0.36 times 222.2. Okay, I'm going to factor out so that it will be 40 is going to be equal to K bracket 0.36 minus L1. So I have 40 divided by K, which is equal to 0.36 minus L1. So this is 40 all over 222.2 is equal to 0.36 minus L1. So this is 0.180 equal to 0.36 minus L1. So L1 is going to be 0.36 minus 0.18. So L1 is going to be 0.18. So 18 centimeter is there the option because this is in meter. So if I convert this to meter, how do I do that? I multiply it by 100. If I multiply this by 100, I'm going to have 1/8, that is 18 centimeter. And that is going to be the original length, which is the option there. Thank you for participating in today's class. You can practice more questions using the Examguide app. The app scores and gives a detailed explanation of all the questions at the end of your practice test. You can learn a particular topic of interest with different modes like study mode, mock mode, and practice mode. It also has other features that makes learning fun. It is a must-have for all serious students. Download from www.examguide.com if you don't have it yet. See you in the next class. Don't forget to subscribe to our channel, hit the notification bell, and share the video to people that will benefit from it. Bye.